I just wrote here a small recap from yesterday for restricted Boltzmann machine. Just gonna quickly summarize it. The network has two layers. Has a visible layer and a hidden layer. And the visible layer is used to describe the variables on your data set, and the hidden layer just gives you expressive power. And the network parameters are the interaction between these two layers and the biases, or this magnetic field. And we have this Boltzmann distribution on the full network, and we can get the marginal distribution on the visible layer only. That's what we are interested in, by integrating out, just summing over all the hidden degrees of freedom, which we can do analytically because the interaction are restricted. And what we get is, again, a Boltzmann distribution with this effective visible energy, which has mean field and this correlation term. And so what we're going to look today is essentially how to learn those weights and biases, this lambda, to do unsupervised learning, so to learn an unknown distribution. Yeah. So, all right. So again, we have a data set, D, is a collection, not X anymore, collection of visible samples, Vk, and they are distributed according to some unknown distribution Q of V. And we want to minimize the KL divergence between the unknown distribution and the RBM distribution on the data set, essentially. So the cost function, same as yesterday, is minus the average over the data set of the likelihood, so the negative log likelihood. So it's the log of the P of lambda of the RBM over the data set. And then we have a entropy term of the data, which we don't consider since it's constant. Okay, so if we plug the expression for the distribution, we obtain is the average in the data of this effective visible energy. We take the logarithm plus the logarithm of the partition function, okay? Just simply by using this expression here. So we have two terms. The first term we can compute. We know how to get this effective visible energy directly, this one here. And the second term is the intractable part of the likelihood. So it's the logarithm of the partition function, and the partition function is the sum over all states of this distribution here. So we can compute it. Because the phase space is exponentially large, right? So in practice, we cannot estimate the cost function efficiently, which is one of the tricky part with the RBM. Like when we have if you are in a network and you want to get an estimate of how good you're doing, you can just compute the misclassification rate as you did the other day. Then you can do it very efficiently, but here we cannot. So there are ways that we can get an idea of how good we are doing, but they are different than computing directly this C. But we don't necessarily want to compute C to get the training going and the learning signal. What we want to compute is the gradient of this cost function. And as you will see, we cannot compute C efficiently, but the gradient, yes. So we take the gradient of C with respect to the parameters, C of lambda, okay? And so this is the gradient of the visible energy and the gradient of the partition function, okay? So at the log, so we have again plus 1 over z, then the sum over all possible visible states, and the gradient of the e to the minus epsilon. So we get e to the minus epsilon of v, and the gradient of epsilon of v, and then we have a minus sign here from the exponent, right? So this is similar to what we have encountered for the regular Boltzmann machine. You remember we had these two terms. One was easy to compute, and one was hard. And so this is essentially the same. So we can write this as the average of the gradient of lambda of the epsilon on the data minus the gradient of the average of the gradient of epsilon over p. Same thing, right? We have the positive phase and the negative phase of the learning. Okay, so yesterday we had correlation function, this xi and xj. Here is going to be a little bit different. We have to take the gradient of this epsilon, but this is fairly easy. I'm just going to do it once. We can take the, well, let me just grab this. So we have three types of parameter. We have two biases and the weights. So we can say the gradient with respect to the hidden bias, that's the bias connected to the hidden, let's do the visible first, to the visible bias. Okay, we have to take the gradient of this with respect to b, but this is just v. So is minus vj, right? Just this term here. We can take the gradient with respect to the hidden bias of epsilon of v. That's the second term. We have the minus the derivative of the logarithm, so 1 plus e to the sum over j of this term, and then the derivative of the exponent, right? E sum over j by j plus ci, the derivative of this is just 1. Okay? And this, you know, if I multiply everything by e to the minus this, I get minus the sigmoid function of the argument, sum over j, wij, vj plus ci. And this is the same function that we had for the activation of the feed-forward the other day. And similarly, we can take the derivative with respect to wij of epsilon. And this is just going to be minus the sigmoid of this same argument, j, ij, vj plus ci times vj. So we are now, when we differentiate the exponent, we pull out the vj out. Okay, so that's very easy. So essentially, when you compute the gradient of the cost function, you just, depending on which parameters you're updating, you're going to use the correct derivatives there. They can all be computed very easily. So the point is that now, again, we have these two terms, negative and positive. And the positive is trivial, right? Just run over the all data samples, and we will see that you don't really use all the data set, but you divide it in batches, like the other day. But the point is that this, once you have a particular v of the data set, you just use one of these expressions for the derivatives, and that's just all there is. The problem is that the tricky part is the negative phase. Just go here. So what's the negative phase again? This is the average over all states described by the model, right? So let me write this again. This is 1 over z. It's the sum over all state of e, well, let me, yeah, minus 0, v of the gradient of the epsilon. Okay, so these sums run over all the phase space. So it's exponentially large in the size of your visible layer, so you can only do it like exactly for like a very small system. But this is the same problem that we faced in the first day. You remember we had the Ising model, and we had this, we wanted to, you know, draw sample from the Ising partition function to compute observables, and we had this exponentially large sum. And we learned that this is, this problem can be solved, can be attacked using Monte Carlo. So we're gonna essentially follow the same approach here, using Monte Carlo. So we want to approximate the sum as a finite size average, let's say L over n of the argument. Right, you remember we defined this general O in the first day, these observables. In this case, we have this gradient, V of L, and these samples VL are drawn from the RBM distribution. Okay? And so again, we can do this in many ways, and the general way that we have seen on Monday was the Metropolis algorithm, right? You remember we had in the Metropolis algorithm, say, we build this Markov chain by doing like a sequential update, and essentially from a state, say V, to a state V prime, we have these two terms. We have a proposal, G, V in V prime. That's essentially the step that, you have this state on the visible layer and you propose a different state in your Markov chain. And then we have the acceptance ratio, V in V prime. And the update you were using for the Ising model was a single spin flip. So any state, this was the Ising configuration. You were like picking a random spin in the lattice, flipping it. This was the G. It was like uniformly distributed overall spin. Yeah, this was like 1 over n for the Ising. And then you were computing, you said if the energy was lower, you were accepting this update. Otherwise, you were comparing a random number with the e to the minus beta and the difference in energy. Okay? So this is like a generic strategy, but in this case, we have this special structure of the graph. And this is going to help us essentially using a more efficient sampling algorithm based on Gibbs sampling. And so let me recall quickly what Gibbs sampling was. This is very handy, I like it. Okay, so the difference between essentially, well, we've seen that Gibbs sampling is a specific case of the more generic algorithm, but the point was that we were sampling from a conditional distribution instead, and then accepting the state that we drawn from that distribution with acceptance ratio of 1. Okay? And so the power of Gibbs sampling is essentially based on the conditional independence of your variables. And the graph here is going to give you like a powerful conditions. So like Gibbs sampling. Right. So remember we had this x was x1, then we had some xj, xn, just being general here. And Gibbs sampling is based on essentially selecting xj from the distribution. So we select the xj in this particular variable, and we select the distribution here, xj, given, remember this notation, x vector minus j. So let me just like write it explicitly. P of xj given x1, x2, xj minus 1, xj plus 1, xn, okay? So we take one of these variable and we see what's the conditional distribution between this variable and all the rest in my system, okay? And essentially, conditional independence in generic like graphical models is, you just look at the graph and you see right here, right? There are no connection between these two variables. This means these two variables are conditionally independent. That's just. And so for the RBM, say let's make an example. We want to sample like a visible unit particularly. So let's sample this unit Vj. Okay. So what we want to essentially sample from and look at is the probability. This is P lambda, the RBM distribution of Vj given all the rest. I say, well, what's the rest? It's V minus J, okay? The visible area minus this, but then we also have the other, the H, okay? Let me see, yeah. So, you should convince yourself that essentially this term here doesn't really matter because there are no connection, but let me just show this. So again, we can use the bias rule, and no, we can write this distribution as the joint distribution between all of these variables. So that would be V of H, but let me just write Vj, V minus J, that's same as V, and H. This is divided P of V minus J H. I just turn this around using like bias, okay? But I can again use the same rule and write this again in the following way. And by P of V J H, sorry, given H. Essentially, I want to isolate the visible and the hidden layer. So I bring the conditional here, P of H, and this is P of V minus H given H, P of H. Again, same trick of bias. These two cancels. But these are now conditional independent. So like, you know, when you have joint distribution of two variables that are independent from each other, they factor, right? So we can write this as P of Vj given H times P of V minus J given H. Then we have P, sorry, I forgot all the lambdas, but you know, better. V minus J given H. And so these two things cancel and you're left with that, right? Just, which is not surprising, okay? Well, these things are not connected together and the distribution factorizes. So sampling one visible unit, to sample that from the conditional distribution, you're just gonna need to consider the state of the hidden layer, essentially. Okay, just gonna move here. I want to keep the first board. Yes?
Can you write a little bit?
Oh, yeah, yeah, sure. Yeah. Okay, so essentially, if you want to sample Vj, we're going to look at P of Vj given H. So all the other visible layers, they don't really matter when we are sampling one particular unit. We want to sample this one here, we're just going to look at these two states here, which is connected to it. This is like a general rule when you're looking at probabilistic graphical model. Okay, so what is this? I'm going to compute this just for this visible, and then for the hidden is going to be the same. And in particular, let's pick a value. Let's say, okay, what's the probability of finding this visible unit into the state 1? Okay. Okay, so let's do this. So again, bias rule, same thing. You have gonna use this over and over again. This is the P that the visible unit J is equal to 1 joined with the H divided by P of H. Right? Product rule again. And this particular distribution is just the, you know, it's just the, let me write here, P of, so we don't know what this is, right? We haven't computed, but we know that this is equal J equal 1 given H. This is the marginal, so it's the sum over all V of P of V and H. Okay? And so we know what this is, right? It's this one here. Again, we can do the same thing here. Here we have a conditional distribution of the visible unit in J given H, and we can rewrite this in terms of the full distribution just by integrating everything else out. So this is the sum over all the other V minus J. So
there is not the condition of the joint, no? That one is not the condition.
sorry, here this is a, yeah. Oh, no, you're right. Yeah. No, good, thanks. Yeah, thanks. Yeah, so this is the joint, yeah, right. And again, same thing I did here. You have the probability over H is the same of integrating out all the V from the joint. I'm gonna do the same here. I'm gonna sum over all the visible units minus the J from the original one. So V minus J, and you have P of V1, Vj minus 1. Then we have the Vj, which is equal to 1, Vj plus 1, Vn H. And below we have sum over V, P of V and H. Sorry, I forgot all the lambda. Okay, is this clear? Like, is there any question about this algebra? It's just like, again, using bias, product rule, and using essentially the marginal definition of distribution. Okay. So bear with me. It's good to do this once, and then you don't have to do it again ever, hopefully. Okay, right. So we can just plug the expression for these two distribution. Okay. So. Okay, so the P, I didn't write the energy, but if you remember, we had minus V minus J, okay, and of the full energy. But the visible unit on the J unit is fixed to 1, so we're just gonna put 1 in the energy. So we get E to the Bj plus sum over I V I J H I. So here I use the fact that Vj is fixed to 1. So here you remember there was a Vj multiplying the bias and a Vj multiplying the interaction. I just set it to 1. And then we have all the rest essentially. So E to the sum over, let's call this K different from J of Vk Bk plus sum over I and K different from J, Wik Vk Hi plus sum over I Hi Ci. Okay, so this was the full energy. I just pull out the J term from this sum and set the visible unit to 1. And below we're just gonna have the sum over V of the same thing, but now general Ci Hi W Ij W Vj Hi J Vj Vj. And so we can, first of all, we can cancel this with this. Yes. Right. Okay, we're just using the expression for the full energy and just put it there. Now we're gonna essentially integrate that out. Okay, let me cancel this. P of Vj equal to 1 given H again. So let's see. So this doesn't depend, so we put it in front. E Bj plus sum over I I. And then we can sum the V. We can just do the summation here. I'm not going to do all the steps, otherwise it's going to take, but then you can work them out by yourself. But this is similar to what we did in the first day, yesterday, sorry. You just sum over one variable and you keep the other as a variable. Okay. So like essentially what you have here is that you have the same product on the denominator as in the numerator except one term. So this essentially reduces to this. This is the same thing, Ij, Hi, and then here you have 1 plus the same thing, which turns out to be the derivative. This is the sigmoid of the argument. So essentially, the probability of having this unit turn to 1 is equal to the sigmoid of the input signal that it receives. So look, if you go to visible unit J and say what's the probability of this being 1, remember these are stochastic variables, so they're either 0 or 1. Then you compute all the signals you receive from all the hidden units that is connected to. You sum it, you sum the bias, and you compute the sigmoid. So this is essentially the same of the feed-forward neural network. But in this case, this is not. That's what the question the other day about the ReLU. This is not something that we impose as an activation function. We say, well, we choose the sigmoid rather than the ReLU. This is something just naturally emerged from the definition of the Boltzmann machine. Okay? And so the other is essentially equivalent. We have P of Hi equal 1 given V. This is going to be the sigmoid of the signal that the hidden units receive, right? So it's going to be sum over I, sorry, this is I, J, Vij, Vj plus Ci. And so this essentially gives you the rule to sample the whole Boltzmann machine, in fact, but each single unit, okay? So the most straightforward thing to do to draw samples from this machine would be to, from an initial state, just pick one of these variable, you look at the input signal, you compute this probability, this you can compute it exactly, right? This is going to be a number between 0 and 1, you pick a random number, and then you sample that accordingly. If the probability, it's very high, this is going to be to 1, other way around. Then you pick another variable at random, and you keep doing this, and you sample from this conditional. Yes?
So instead of having a neural network that has activation functions as neurons of the whole neural network, you have a neural network that only depends on the input data, and then postulating this assumption of creating a probabilistic model, it's implicitly the model that there is the sigmoid function.
So the question, I guess there is another room, right? Yeah. So the question is that instead of postulating some activation function in the neural network, I mean you define a probabilistic model at the beginning, and this just the rules are implicitly from the initial model. Is that correct? I understood correct? Yeah. Yeah. Exactly. Yeah. So essentially, we define an initial energy function here. And then when this energy function dictates what's the probability we're going to have to sample. The same thing that we did with the Ising model at the beginning of the class. We have some energy function, and then when you do Metropolis, you're going to have some acceptance ratio which depends on this initial model. Here is the same, essentially. Yeah. So this is an Ising model. The Boltzmann machine is exactly an Ising model, just defining a different graph, played by some different rules, but that's what it is. That's why, I mean, it was adopted by the physics community and exported in many, many different problems very easily. Yeah, okay. So yeah, we could sample this way, right? We could pick random variable in the random units in the graph, compute the conditional probability, and then update with acceptance equal to 1 with one of the two states. And that would be fine, but we can do better. And we can do better because the two layer are, the units within one layer are all decoupled from each other, right? So the point is that now we looked at the probability of having just one, but let's consider the probability of having the full state given the full, visible given the full hidden layer, right? So this you can prove, it's very easy. Factorizes over the visible in the unit. Same thing for the other. I will forget this. H given V, this factorizes. I mean, you can see from the graph, H I given V. Okay, I mean, this again, if you look at the graph, this would be, it kind of makes sense. But again, you can use bias and write this as the joint distribution and see that this factorizes and then go back to the conditional. And so the point here is that since these decouple this way, then when we sample one visible unit or the other, these two processes are completely independent as long as we fix the hidden layer, right? So if here I change J, again, this doesn't depend on all the visible layer, the other visible units. So the key point here is that we can do this all in parallel. So we can essentially build a Markov chain that starts with some visible state, V of 0, and then update a hidden layer just at once. And we can do this parallelly just like in the computer, just by doing matrix and vector multiplications. And then from here, we sample a new visible state, V1, this is H0, and then a new hidden state, and etc. H1. And so this is called block Gibbs sampling. And this is another reason why we restricted the machine at the very beginning. Like, one was that we could compute this in a tractable way, but we could have kept the connection in the visible layer. But if we do this, this variable wouldn't be conditionally independent, right? And we couldn't do this block Gibbs sampling. And this is very fast, right? Imagine having, like 1 million visible units, and then Metropolis, you would have to sample all of one by one. But with Gibbs sampling, you sample all 1 million like in one step, just all in parallel. So it's a big deal. Okay. So let's get back to the negative phase, right? This was this gradient, which we approximate as 1 over n, sum over L goes to 1 to n, of the gradient of the visible energy for these samples, where, VL are sample from P lambda of V. And essentially, we're using bulk sampling, in the Metropolis language, our proposal from V to V1, V prime will be the product of P, P of V prime given H for P of H given V. So to go from one visible state to the next one, from here we sample the hidden layer, and then from the hidden layer we resample the visible layer. So there are 2 steps, from here, sample, and sample, and you keep doing this block back and forth. That's this block Gibbs sampling procedure. Any question about the sampling? Yes.
I understand that this is what is also called alternate Gibbs sampling,
Mm-hmm.
because you just keep changing the hidden units and the visible ones in a binary way.
Yeah.
Is there a situation where this can't be used?
You mean like for the RBM case?
Yeah, for a physical system that doesn't allow us to use this method of sampling.
So this particular sampling works because of the structure of the RBM. So every time you have two, what? Repeat the question. So the question was like this particular alternate Gibbs sampling, in which situation this cannot be applied? Okay, so this works for the RBM because of this structure. So if you have two sets of variables we are talking about graphical models. If you have two sets of variable that they are conditional dependent between each other, but each set separately they don't have any conditional dependence between its unit, then you can always do this. So essentially here we are identifying these two sets, H and V, and there are no connection between these two. So in practice we could have, and this is called the semi-restricted Boltzmann machine, we could have add connection here, then we can still do this sum because there are no connection in the hidden. So it's still a tractable model, but if you do this, you actually increase your expressive power, but then you lose this sampling. Then when you sample, you can sample this, but then when you do this step on the sampling, then you can't do it in parallel because these are conditionally independent between each other. So, okay. So there is a last ingredient, and then we essentially have the whole picture for the training algorithm. So the sampling, the Gibbs sampling, is powerful, it's fast, but imagine this, when we train this model, we are doing many iterations, like in the feed-forward, right? You do one step, you compute the gradient, you update your parameters, and then you repeat. Now, to get the gradient, to update the parameters, we have to compute this, okay? And we have to do this at every training step. To get this, you remember, when we sample, there is this transient at the beginning where our samples are not really distributed according to the stationary distribution, so we have to equilibrate or do this burning, right? You remember the first day, we have this 10% of the steps. So you start from a random sample, then you have to equilibrate to the stationary distribution, then start your sampling. And you have to do this at every iteration because the model change, the parameter change, so your stationary distribution also changes. So it's a very cumbersome process, okay? But there is a way out, essentially. And the way out is essentially to consider a different cost function. So what we were considering was the KL between the data and the model. And this is your stationary distribution. And so the breakthrough algorithm that allow RBM to be learned very efficiently from Hinton was instead, it's called Contrastive Divergence. Maybe some of you heard this before. And instead consider this cost function. Is the contrastive divergence is like a difference between two KL, the KL between the data and the model, minus the KL, and I'm going to explain what this is now. This is the KL between the probability distribution of your model after k steps of block Gibbs sampling. Okay, I'll explain what this means. So the point here is that what you want to avoid is to do this long equilibration to your stationary distribution at every steps. This is gonna just slow down your training and you'll be in trouble. But there is kind of intuitive. I'm not gonna. There is a proof, and there are theorems about this. I don't want to go there, but I give you a kind of intuitive explanation. So you can prove that this quantity is always positive because the k steps the probability after, the probability distribution after you do k step of sampling is closer to your stationary distribution than the data. So the point here is that you initialize your chain from a data point and you do some step of Gibbs sampling. So this is gonna bring your state away from the data and towards your distribution, your stationary distribution, right? So by updating the weights and your parameter by minimizing this, you essentially trying to remove the tendency of your block Gibbs sampling to leave the data distribution. So I know it's like not very precise, but there are, this can be proved in a more formal way. I don't think it's not like, it just would take a long time. But the point is that even by doing a small number of steps, even with one steps, that's what they usually do. They do one step of sampling. So they start from the data, they do one sampling step, and then they update the parameters. And these two sampling steps, they're gonna, bring your distribution away from the data, and you're trying to bring it back, as like updating the parameters, essentially. And so this is called contrastive divergence. And essentially, when you take the gradients of this, you can see that the gradient of CD, okay, is the positive phase as before, minus the same gradients after k steps of sampling. So that's our learning rule, essentially. Every training step, we initialize our block Gibbs chain with a data point, we do k steps, and then we measure this and we compute the gradient. Okay, so let me just kind of summarize all the parameters and the steps that is going to be useful for today's tutorial. And so in today's tutorial, essentially, all the RBM code, you won't really work on that, but you're going to play with these hyperparameters and see what effect they have on the learning. But you won't be coding the gradients or anything of this. Okay, so what are the hyperparameters that you're going to modify? Okay, so we have the number of hidden units. Okay, so essentially this is your expressive power, M. The more hidden units you have, the more powerful is your network. But beware that if you have too many, the optimization might become more difficult. So again, there is a sweet spot in this number. Then you have these steps. Yeah.
So in contrastive divergence, the next term still involves exponentially many summas.
No, so it's still this negative phase here. The last term is still approximated by a finite size sum. The point is that instead of equilibrating to your distribution and then collecting your statistics, you just do a few steps, like 1, 10, and then you do that. But the point is that you have to start from a data point. You can't start from a random state. So you start from a data point, and then you just sample a little bit. And you can imagine that if you're converged and your training is optimal, then you're going to start from the data sample, and as you sample, you're going to stay in the same distribution because you learned that, essentially. Yeah. And so exactly, the second hyperparameter is the step of this contrastive divergence. So, I mean, one is a value that was used in typical machine learning application. I mean, we can do a little better, maybe like 10, 20, that's really another parameter to tune. Then again, we have the learning rate, like gradient descent, and the batch size. So I don't remember now, were you using like a batch size? I imagine so, when you were training the feed-forward neural network, right? Or not?
Yeah.
Yeah? Okay, so this is for the spirals. No?
For the bonus tutorial, yeah.
Okay, so it was in the bonus tutorial. So essentially, okay, so this is the other thing. When you compute the positive phase, you're doing the average over the data. Now, you don't want to average over the full data set, right? This is going to be thousands, possibly 100,000 of samples. You just want to use maybe a small subset. So maybe 100, 10, 1,000. Again, this depends on many things. That's another hyperparameter that you have to optimize. And then there is a regularization that I don't know if you're going to use today. And this, if you remember yesterday in Juan's lecture, that's this extra term that we add to the cost function to like essentially encourage like small weights and don't overfit. So in practice, when you have to train and learn an RBM, you should like try to find the optimal values for all of those. There are other that, you know, if you use more sophisticated updates, then you're gonna have other hyperparameters, but we're gonna like keep it simple, and there's still like a bunch of them. So that's kind of the goal of today's tutorial, kind of learn to navigate this hyperparameter and see what is the effect. So typically, you know, if you put the learning rate very small, then it's gonna take much time to get to your optimal. Maybe you're never gonna get there, but if you put it too large, then you might bounce around the landscape. And same thing with a batch size. If you have a very large batch size, your training is less stochastic. If you have a small batch size, it's more noisy, but sometimes noise helps you escape local minima. So it's like, yeah, there are many angles to this. And so yeah, let me just sketch one step of the training, what's going on, just to summarize. Okay, so this is one training step. So the first thing is that you select a batch of data. This is typically done at random, okay? And the size is the hyperparameter. Then you compute the positive phase. This is this average of this gradient with respect to your batch of data. Then you can do in the size of the batch. Second, you initialize the Markov chain with the data. You run Gibbs sampling. These all functions today, they're already written in the code. I think you just have to call them. Gibbs sampling. Then you compute the negative phase. So you run the Gibbs Gibbs sampling, and you're gonna get some statistic at the end, and then you use it to compute the other term. And finally, you update the parameter. Okay, any question so far? Maybe time for question, then we can.
Can you write down the regularization? Which regularization is used in the
Regularization?
Yeah.
Yeah, so that's, I think we use regularization in the code, but a typical example is like just the L2. That would be lambda W transpose W. So that's just the square of the weights. Yeah. But there are others. There is L1 But I think we use L2 in the code, or maybe we don't even use it. So the point is that we're gonna have our data sets are gonna be very large. Our data set is gonna be they're gonna be large, so you don't necessarily need regularization if you have a very large data set. If you lack data, then yes, because if you don't have regularization, you're gonna overfeed the data you have. If it's not a representative statistic of the full distribution, then you're in trouble, essentially.
Do you think that your representation of this new neural network, because for me it's new, can be represented by the usual or the standard model of the neural network, that is the first layer is the input, the second layer is the activation function, and the third layer is the output of this operations?
That's a very good question. The question was, can the restricted Boltzmann machine be represented as a regular feed-forward neural network? And I didn't think so for quite some time, but the answer is yes. Essentially, you can, let's see if I can remember. So you have your input layer would be your V. Then you would have your hidden layer here. And now you have directed connections. So this would be like a feed forward. And your activation function on this layer would be the soft plus, right? Like a log of 1, so essentially the same. And then you have only one unit at the end, which is the P of V. But this is called, what's called in machine learning community is called skip connections. So you take this state and you skip this layer and you use the visible bias. Am I right? Right? Yeah. So that's really cool way to see this. There is no sampling here. You just propagate the signal and you get a P of V. You cannot use Gibbs sampling here. You cannot use this block Gibbs sampling. So you lose that. You have a P of V, so if you want to sample this, you have to use Metropolis. So that's essentially why we don't use this, but it's a really nice way to kind of see the network. Okay.
What is the advantage of the Gibbs sampling?
Sorry, come again. What is the
advantage of
the advantage?
Of this?
The advantage is that essentially you can sample all your visible unit in one step. So say you have this, right? And you want to sample from this distribution. Then you need to find, first you need a proposal, this G, that brings you from one state to the other. And this single spin flip for the Ising model, it's a good choice, but it's not always good. So you have some insights on your model to like devise a good selection, a good proposal. And yeah, you could use maybe cluster updates to sample more than once, but then it would depend on the probability itself. So when you do like cluster update for the Ising model, you devise them because you know the Ising Hamiltonian. So in general, if you have to do something like that, you have to study this network. So it becomes more involved, and so that's why we use Gibbs sampling. It's just like very fast and efficient. Okay, yeah. Are we taking 5 minutes or
yeah, we can
are we
take
going
5
straight?
minutes.
Yeah, okay.
So, you want to use some kind of physical object to simulate physics as opposed to simulating in silicon programming, to really be that physical object that will give us
This is like neuromorphic computing.
yeah,
right?
exactly, something along those lines, exactly.
Yeah, I don't know much about that, honestly. But I guess it would be with some, I don't know, maybe Roger, if you can simulate with this neuromorphic computing, if you can build this, or people are doing this.
No one's ever successfully trained, I think, a neuromorphic chip on this. But they've successfully implemented them and sampled them.
Okay. All right, so I'm gonna get started again, and this last lecture is gonna be more like research, like oriented. So we're gonna look at like an application of all these RBM business and unsupervised learning to like quantum, many body physics, in particular quantum state reconstruction. And so the question here that we are asking is the following. Right, so can we learn a quantum state from measurement data? Okay, and so this is it's a very old question, and the answer was quantum state tomography. I'm gonna comment on that, but it's really important for like many different areas. And so, in one important application is in condensed matter, especially for quantum simulation platforms. And the reason is that imagine you go into the lab and you build an experiment. Say you build an experiment to simulate the Hubbard model or some strongly correlated material, right? Now, there is only so much you can do in terms of measurements, in terms of control. So the idea is that if you get access to the quantum state of your device, of your synthetic material, then you can, you have almost like full access to all the measurement that you're going to do. If you have to measure in the lab, then this usually have some overhead in the experiment. So there are typically some things that you can measure very efficiently. Some other things that are very costly. It's possible, but it would be like a big experimental overhead. Some other thing that you just can't measure in the most of the times, like entanglement. Entanglement is something that is very, very hard to measure at the level of the experiment. Okay. So definitely being able to just do some simple measurement on your device, say you measure if a qubit, or well, we are talking about condensed matter. So if an atom is in the ground state or the excited state, and just do this measurement, like feed them to the neural network or whatever, this is a black box, and this gives you the quantum state, that would be like very desirable, right? And then you can think of like in terms of more like quantum technologies, so quantum computers, quantum hardware, then typically the goal is to run some quantum algorithms in this device, and so you have some initial state and some output state, and you need a tool to do analytics, like to verify that you're doing the correct thing, essentially. So you want to know, is the quantum state that I'm preparing, the quantum state at the end of the hardware, the one that I actually wanted to prepare? And so quantum state tomography or quantum state reconstruction is another, even in this case, is a tool essentially to do that. And I'm calling quantum state reconstruction and not using the word tomography because, so when I talk about tomography, what I mean is some kind of an unconditional technique that I give you some measurement and you're gonna give me the quantum state which best resembles this measurement, no matter of the quantum state. So there are no conditions on that. Instead, we're gonna put a prior condition. We're gonna assume that the quantum state has some structure, and the structure will be encoded in the restricted Boltzmann machine, and so that's why I call it reconstruction. So it's not an unconditional technique. Not all quantum state can be reconstructed with a neural network. If it's like a very random, chaotic state, like good luck, essentially, because machine learning needs this structure that you have seen in the data. Okay? And so, let's consider quantum system, and let's consider closed and isolated system. And with closed and isolated, what I mean is that essentially it can be described by a pure quantum state, a wave function, okay? So this is the object that we are interested in. And so what we do, we can write this wave function into some basis. So essentially we are fixed a reference basis of the Hilbert space. No. we have n degrees of freedom. This could be qubits, or could be electrons, could be atoms. And we fix the basis of the Hilbert space and we expand the wave function in that basis, okay? So for spins, this could be the quantum number on the z direction, like sigma z. If you have like particle hopping on an optical lattice, this could be like the occupation number in like a second quantized formalism. It doesn't matter, so we just stay general. We have this basis and then we have this expression of the wave function. And so quantum state reconstruction essentially means obtaining this coefficient from measurements, from data. If I have these coefficients, essentially I have the full state. Of course, there are exponentially many. Again, imagine these are qubits and these are like zeros and ones. Again, we are back in this phase space with 2 to the n state. That's why quantum mechanics is hard, right? Because the state lives in this Hilbert space, which is exponentially large. So we can't, contrary to quantum, the conventional quantum state tomography essentially builds this full vector. Usually it's done on density operators, so you have a density matrix, and you construct the full density matrix or the full state, and then you try to learn all these coefficients. But we're gonna define a representation of the state which is efficient. This means we don't need this exponentially many number to encode the state, and this is gonna be an RBM essentially. And then we need the mean to extract this coefficient from the data. And this is like simply, given by essentially the Born rule. This is the way that we connect quantum state to probability. So the Born rule tells us that if we do a projective measurement, so if we collapse the wave function in this basis, the probability P of observing some of this state is the absolute value of the projection of the wave function into that particular state squared, which is just, this square. So this is our link from the quantum state to the probability. And I mean, we have seen that we can learn probabilities from data, okay? So this is kind of the idea. And data here means that if we, one requirement to do this, like clearly is that we need to be able to prepare this quantum state many, many times, okay? And we prepare this quantum state, capital psi, we don't know it, and we do a projective measurement on this basis. And what we obtain is essentially one of these state. Let's call this sigma 1. And then we do this again. We prepare the quantum state, it's going to be in some superposition, we collapse the wave function, and we obtain another state. And we do this many times, and what we end up is a data set of sigma. Well, I'll be consistent with the previous notation. Okay? And we know from the Born rule that the probability distribution of this data, of these projective measurements, is P of sigma. Okay, so if we could learn this distribution, then we would have access to the quantum state. And so I'm going to make another assumption. This is very stringent, but to keep it simple, essentially. I'm going to assume that the state that we are trying to reconstruct is real and is positive. I know, it's not true for most of the matter that we know. But for this, these assumptions can be relaxed. And if I have time at the end, I'll just tell you quickly. But this is the first step, and most of the matter does not really respect this condition, but there are some cases where the quantum state indeed has this structure. And so, as you can imagine, if these two conditions are true, then there is a one-to-one relation between P of sigma and psi of sigma, right? You're taking this number is not negative, is non-complex, so taking the absolute value square is the same as taking the square. So essentially we know that this psi of sigma is equal to the square root of p. Make sense? And this is essentially how we're going to formulate our quantum state reconstruction with the neural network, right? So this neural network quantum state reconstruction means, in this case, let's say RBM, use an RBM to learn P of sigma. Okay, and if this is true, if we find a neural network parameter lambda such that the P lambda of sigma is essentially equal to the capital psi, P of sigma, then we have obtained a neural network wave function psi of sigma, which is essentially the unknown state that we are seeking. This is because this state here, again, doesn't have any phases. That's fine. And so, what this psi of sigma, like neural network psi, is just the square root of your Boltzmann machine distribution. So, if we want to spell this out, e to the minus epsilon of sigma divided by 2. Okay, so that's what I was telling yesterday at the beginning. Like the neural network itself can be used to essentially like gives you a representation of a quantum state if you phrase it this way.
Yes. How important is this assumption that the wave function is real?
Oh,
It's necessary.
it's crucial for this. So, if the wave function is not real, or like negative, with negative, I mean negative and positive. So, if we say that as a sign structure. So imagine like a singlet state, right? Singlet state would be square root of 2, 0, 1, minus 1, 0. So we have a sign structure there. We have a plus and a minus. So if this is the case, then this cannot be applied in this way. So if this is, we have both plus here, then yes.
But you figure out a way to sort out.
Yeah. So I'm taking this example because it's easier and it's easier to understand. And if I have time at the end, I'll show you how we can essentially extend the neural network to capture the phases. And then what we did, we also extended the extended network to capture mixed state. So not just wave function, but density matrices. It's just like a systematic increase in complexity. Okay. So yeah. So this is the question was, I guess, how important is this assumption? And yeah, it's very important because then this is true. And now again, imagine to having electrons. Then if you have electrons, this condition does not apply anymore, and there is mostly electrons around. But there are cases where this condition is satisfied, and I'm gonna make an example and work through that. Yes. Yes. And we're gonna look at the simplest, probably, example of ground state of a many-body systems, non-trivial, which is the transfer field Ising model. And so this model, we consider 1D. We have a chain of spins, sigma 1, z, sigma 2, z, sigma n, z. Spin 1/2, and the Hamiltonian, now the Hamiltonian is an operator, we have, let me say J. J, we have sigma Z, J. So we have nearest neighbor interaction along the Z-axis, and then we have a transverse field. So can you raise the hand if you already seen this before? Okay, so no, okay. So this is kind of, it's one of the simplest, non-trivial, like, model for like quantum magnets. And so if you forget about this, essentially you recover the IZ model the first day, okay? So imagine, okay, so let's set H equal to 0, okay? So we don't have the transverse field, we have a Hamiltonian which is diagonal. So this is essentially, it's like a classical model. And this is the same Hamiltonian we see in the first day. That was 2D, and this would be 1D. But when you're looking at the ground state of this model, what you're going to find is that you have two possible states. You can either have all spin pointing up. This is in the Z direction, or all spin pointing down. Actually, again, this is equivalent to the 2D at 0 temperature. Remember, we had this two polarization. All pixels were white, all pixels were black. And because this is the Hamiltonian is invariant, so we have this symmetry here, okay? And this is for J equal to 1. Ferromagnet. So this is like a quantum ferromagnet. If we have J equal -1, then essentially we would have an anti-ferromagnet where the spin alternates up and down to minimize the energy. Okay, so this is a fully classical state model. But what happens when we turn the transverse field on, right? What happens is that, okay, I'm gonna delete this. Erase this. So let's consider the case where H is non-zero, right? We turn on this transverse field, and now we have these terms here. And recall that this sigma x Pauli matrix, it flips your state, and vice versa. So as soon as we insert this term in the Hamiltonian, we're gonna start having quantum fluctuation. Some of these spin are gonna flip, and as this grows larger and larger, we're going to have more quantum fluctuation. At some point, this ferromagnetic order is destroyed. Okay? And in particular, we have a quantum phase transition at H equal 1. So the phase diagram in H. So this is your classical point. Here you have a ferromagnet, H0, and here you have a paramagnet. So essentially, when you are in the limit of H much bigger than J, then this interaction doesn't really play a role anymore, and your ground state is the eigenstate of sigma x with the eigenvalues +1. So we say this. We call this right. So like right would be 1 over square root of 2 up plus down. Okay? And so when you're in this state and you look at the Z direction, essentially what you find is a completely disordered state. You cannot find all possible direction, all possible orientation with equal probability. Just the tensor product of all these states on the single side. Okay? And so here we have a disordered state, like a quantum paramagnet, and the limit of infinite H. And when we go to H equals 0, we have a quantum phase transition. And this is the same type, for who knows what a universality class is, same universality class of the 2D classical Ising model. These two models can be actually mapped into each other. Okay? This is one of the simple, it can actually be solved exactly, and analytically from this Hamiltonian you can find the exact ground state by mapping essentially to free fermions. And so the difference is that in the previous classicalizing model, the thermal fluctuation drove the phase transition. Here are quantum fluctuation induced by this transverse magnetic field. Okay, and so I'm telling you all of this because the ground state of this model respects exactly these two properties that we had before. So the ground state is real and is positive. All these coefficients in this basis here of the sigma z basis are all positive. Okay, so is this relevant? Can this be done? Actually, can this be found in materials or done in experiments? And the answer is yes. And I just want to make this kind of parenthesis to connect to actual experiments. And so one of the platforms to simulate this type of physics, this microscopic physics, is given by cold atoms, and in particular Rydberg atoms. And essentially this has been done in experiments, and one of the paradigms to solve this type of models in the experiment is that you don't really want to deal with electrons. Those are very hard, but if you can build a different system, maybe not quantum spins, but maybe some cold atomic system that has the same microscopic physics, but then you have way more control on it, then you could use that instead and simulate the model you seek. So this is called quantum simulation, or quantum emulation if you want. And so one platform is given by Rydberg atoms. Rydberg atoms, and these are neutral atoms, and the particular properties of this atom is that they have a ground state and they can be excited in a Rydberg state. A Rydberg state is a state of the atom where the electrons occupy one of the outer shell and essentially has a very large radius. And the point is that the Rydberg atoms interact very strongly with each other through van der Waals potential. So what they do in experiment is that they trapped single atoms with this thing called optical tweezers. Those are laser beams. And they can really assemble this chain of single atoms free of any defects. So this is something of the order of some micron. And they have all single atom. One usual size is rubidium or strontium. So you can trap them and move this tweezer and change the distance between each of these single atoms. It's pretty remarkable. And what you can do is that you can shine a laser to essentially excite this transition from the ground state to this Rydberg state. This will be this sigma x. And what happens is that when you excite one of these atoms in a Rydberg state, and you excite the other atom in the Rydberg state, these two atoms interact very strongly with each other. Okay? So what you can do essentially, you can build something like that out of these Rydberg atoms. And so this interaction here between two nearest neighbor Rydberg atoms would be essentially equal to this one. It would be equal to like an antiferromagnetic interaction. That means that these two atoms, they don't want to be simultaneously in the Rydberg state. So if this is in a Rydberg state, this is going to be in a ground state. If this is excited in a Rydberg state, this might decay. So essentially you can build this pattern. Rydberg, ground, etc. And this is essentially equal to up, down, up, down, up. You know, you have this two-level system, and you can engineer this strong interaction. Essentially, you can engineer this type of ground state out of cold atoms, which is very, very remarkable. And so this is a way that they control and they prepare these states, but then they have to measure. And this is where the state reconstruction comes into play. The point is that in this type of experiment, like one of the measurement that they can do is they can just do fluorescence imaging. So they probe if an atom is in the ground state or is it in the excited state. So they get some picture essentially of the single atoms. And doing this measurement is equivalent of doing this sigma z measurement. So same thing, they can prepare this ground state, image it, get a snapshot of if the atom was in the ground state or in the excited state. This is your data. Re-prepare the ground state, do this again and again and again. And if you do this many times, you're gonna build a data set which contains fingerprints of the quantum state, right? So you can build the data set D. I'm gonna write this again, of a series of measurement of sigma z. Now you can think of sigma z in this way. Sigma z equals 0. The atom was in the ground state. And sigma z equals 1. The atom was in excited state. And this data set, the probability distribution of this sigma z is equal to the absolute value of the wave function. So again, it's our connection between the probability distribution and data and the wave function. If we can learn that, then we have the wave function and we have succeeded in the reconstruction. Okay, but I'm telling you of this because I want to kind of motivate why we have to go to all this trouble. Why cannot we just build this thing, just do the measurement, be done with it? We have to go through a neural network. And so the reason is that there is only so much you can do in experiments. So I'm going to give you two examples of two things that you might be interested in measuring. The first one is the average of sigma z. And we're going to be in the lab right now, non-neural network. So you imagine you want to compute this quantity in your experiment. This will tell you essentially what's the average population in your experiment. So what is this? Okay. So this is the expectation value of sigma z on your wave function. Okay. So I can insert two resolution of the identities here. So this is psi sigma z prime. This is the operator. Let's say on site j, in one of the sites. Then I have another resolution of the identity, psi. Okay, so this is your coefficient, right? These two, it would be complex conjugate, but again, the wave function is real and positive, and this gives you a delta. So you can write this as as psi of sigma z squared, sigma j z. Okay? This operator acts on this state, but this is an eigenstate of sigma z. So essentially it just gives you the value on the j spin and gives you a delta. Okay? And so this is equal to the probability times sigma z j. But we have the data set, right? So this is the probability of my data set. So I can just approximate this sum with my data. And I have 1 divided by the data, sigma z in the data set, sigma j z. And so you can do this. This is how you would calculate this expectation value from your data in the lab, and that would be perfectly fine. Okay? Any question about this? So you're doing this measurement in a basis, and you want to compute an expectation value of an operator which is diagonal in that basis, and that you can do. But the second example is that where the quantum state reconstruction becomes very important, is say you want to compute the average value of sigma x instead. And this is important. It's an important quantity because it essentially gives information about the quantum fluctuations in your state. Okay, so you can essentially do the same thing as before. We can take the average value of sigma x on spin j. as before we have these two sums, but there is an important difference, as you see. The difference now is that you measure in one basis and you're asking information of an observable which is not diagonal in that basis, okay? So when you act with sigma z on this state, it's gonna flip the J spin, okay? And essentially what this becomes, you can multiply and divide by psi of sigma z. So this sigma z here and here, they give you p again. Again, we always want to write this as an average over this probability. But then we have left with this term here. So what's the point here is that you see you have the same thing as before, but before the only thing we needed to know is what was the value of the sigma z in the data. Now we have this quantity here which contains the wave function, okay? And we don't know what the wave function is, right? You could do the frequency distribution and try to invert this relation, but remember we have all this zero. Like the most of the, if we do frequency inversion from the data set, most of this coefficient will be zero. So if you try to do that here, you will get something which is completely off, essentially. So the point is that this is an example of something that you cannot measure if you don't know the wave function. And you could measure in the lab, but it would contain, you know, it would lead to a substantial overhead in your experiment. You would have to do a rotation and apply lasers. But the point is that if we can reconstruct the wave function in that basis, then you see we just need the wave function in that basis to obtain the average value of sigma x. And you know, sigma x is one example, but there are many more. The other one important is entanglement, for example, that you cannot obtain just by the data, okay? Any question here? Yeah?
So a priori one could do this using any, I don't know, kernel-based learning, try to estimate the probability. So the advantage of RBM is maybe that those ratios are easy to compute?
So, yes. The question is if you could use other technique to reconstruct P, and the advantage of RBM if it's in the ratio here, you said?
Yeah, that are easy because the Z cancels.
I would say like the advantage of the RBM, it's in its particular structure, in its particular ansatz. You could just as well use a different neural network. Now we've been exploring like recurrent neural network lately, and seems they even work better. You could use a feed-forward neural network. Of course, like all the reconstruction process will be different, but any representation of psi in terms of, as long as it's compact. And with compact, I mean the parameters that you need to represent psi should not be exponential. So feed-forward neural network are known, sure, yeah. So essentially, again, the strategy here would be use this measurement to find an expression from psi and use this representation that you find through the data to compute other things, okay? Let me see, I want to say this. And you know, we're, in particular in like experimenting in condensed matter, you can use this for many reasons, right? One reason, as I said, is that some of these observables are not available in the experiment, so you can use what is available to find a wave function and then use that to compute other things. But another thing which is pretty important, and you can use it as a faulty detection mechanism, right? There are situations which I also encountered in which you run an experiment, then you do some measurement, and everything seems to work out. But as you look at measurements which are not available, you might find some discrepancy. And so that was one thing that happened to us, that we actually ran this reconstruction for an experiment, and we couldn't really match these unavailable observables with what we expected to be. And I mean, we thought that the reconstruction was not really working. At the end of the day, it was actually the experiment that was a miscalibration, and the RBM actually caught that, which was like pretty cool. And so let me just like mention briefly to conclude like what happens if you have phases, right? And you know, like this is in some sense like phases in a wave function, and with phases I mean that your psi of sigma is complex, or your psi of sigma can be both negative and positive. I mean, this is somehow is what makes a quantum state truly quantum, if you want, right? So, like, the sign structure is at the heart of Pauli exclusion principle for electrons. So, two electrons cannot be found in the same quantum states. So you have all this amplitude with different signs so that it cancels out. This is at the base of quantum interference, for example. It's at the base of essentially the most of quantum algorithms. So it's very important, and we can capture it really with this framework. And so there is an easy way to essentially do the same thing for complex wave function, is that we just take our neural network wave function and we add a phase term. It's just that simple. So imagine that we had this neural network, this RBM. This is our sigma, this is our h, this is our wave function, and a simple way to essentially add a phase is to add another hidden layer. And so this is a recurring theme, is that if you need more than what the RBM gives you, just keep adding hidden layer, and you can extend this reach. And you know, you can, I mean, I could go through the derivation of the tomography for the complex phase, but it's pretty long, and I don't know, maybe we could look at the tutorial instead and get ready for the next hour. Just take a look at the tutorial instead.
Ah, okay.
Yeah, so yeah, I'd say so.
Okay.
Yeah. But here? Yeah, okay. So let me say this. So before, essentially, we had our wave function. So if we fix a basis, we have a neural network wave function. And so far, this neural network wave function was the square root of the probability distribution. Okay? But this clearly cannot be negative or complex. So like an easy way out is just that you add here a phase term to make it common. And this is another neural network. Now you have freedom in choosing this phase term. It could be, what we used originally was another RBM, or better, like another hidden layer in the RBM, so that you had one visible layer, one hidden, and some v lambda. That
How an RBM produces a probability distribution.
yeah.
The data is no longer that. It's a function that is not.
So So you can define this theta of mu as a log of p mu of sigma. And so we had like one hidden layer for the amplitude, and this was W mu, and one hidden layer for the phase. The trick is that when you use these connections they don't have the same meaning. You don't use them for sampling, essentially. But you could use a feed-forward neural network the same way. Again, it's just a function. So you can choose whatever you prefer. And the other difference is when you run this reconstruction for complex, then it's pretty important, I should have mentioned that. If you have the target wave function is this psi of sigma, which is also complex, and when you measure p of sigma, you're taking this absolute value, right? So if you measure in the basis that you're trying to reconstruct it, you lose all the information about the phases. You lose all the information about the sign. So like this is not sufficient anymore. Now, the way to do it is essentially that you need to, before doing the measurement, you need to change the basis. And this is all is other thing, and the amount of basis that you need and the amount of rotation depends on the state, but this is pretty involved, I'd say. So we're not going to cover this in the reconstruction today. We're just going to look at the classical state, but the code that you will use today, it can be used directly to reconstruct positive wave function.
Please see if there's questions from the audience.
If there are other questions here too. Oh yeah, let me write this down. So we have a software that we developed at Perimeter last year, and you can use that. There are tutorials to do the reconstruction for both positive and complex phases. It's in Python and it's based on PyTorch, and it's called Cucumber. Well. It's a quantum calculator for many-body Eigenstein reconstruction. Did I get this right? Well, and is this in pickle?
Yeah, it's in pickle.
Yeah, okay, we have it in Slack. Other question there?
No.
Okay.
Question.
Yeah, so I don't know.
We can break.
Yeah, we can break now.
We'll take the group picture and.
Yeah, it's good. Yeah. Okay.
Right. So let's thank our speaker then.